Up to this point, we have been working with one sample, like the fruit snack. There was one sample, there were 4 outcomes, but it was one variable. In 9.2, we talked about 2 variables, gender and highest education level achieved. What happens when you have more than 2 variables? What if you had 3 or more sample variables, 3 or more means that you wanted to compare? How would you do that? This is called an analysis of variance, or an ANOVA test. And what an ANOVA test does for our case is we are working with means. So we are working with the mean of a data set, the average. We're back to mu's, but we've got mu1 and we have mu2 and we have mu3 and we have mu4 and we have mu5. We have multiple data sets, and we want to compare the averages of all these data sets and determine whether or not we can say the averages are the same. Are the averages the same or are they different? In order to do this, there is a lot of complicated mathematics, a lot of complicated mathematics. And this is kind of the tipping point where introductory statistics kind of stops and more advanced statistics starts taking over. And when you get into more advanced statistics, you cannot do it by hand. The graphs are much too complicated. The mathematics is much too complicated, as you're about to see. And we really rely on spreadsheets and specialized software in order to calculate our p-values. So we're still doing hypothesis testing. We're still looking at p-values, but the mathematics becomes more obscure. As a student, you will become more disconnected from the process of finding these numbers. It's just going to be copy and paste this data into the spreadsheet, press a button, and write down your answer. You're not going to be able to follow the mathematics involved here. Now, if you take an advanced statistics class, this is what you'll be studying. You'll be studying more about where these formulas come from. And so, for example, we're no longer dealing with a z-score or a t-score or a chi-squared score. We now work with an F distribution, like they're running out of letters in the alphabet. So they just call this an F distribution. Okay, so it's not a normal distribution. It's not a t-score distribution or a chi-squared distribution. This is called an F distribution. And its graph is crazy. There's all different kinds of graphs for this. And this is because we're dealing with 3 or more data sets. And so our null hypothesis is going to be that the mean of all the data sets is equal. So the average of all the data sets are equal. The alternative is that at least 2 of the means are not equal. We still have a significance level, and this is great. So how do we calculate this F score, the F score to be put into the F distribution? Well, it's based on this, which is this calculation, and it's divided by this, which is this calculation. So you got fractions within fractions. Well, how are these calculated? Well, the SSW is all of this stuff, and the SSB is all of this stuff. Again, you start to disconnect with the mathematics. Like, you can follow the pieces, but how they all fit together is difficult to understand. You then get a p-value, and you compare it to alpha, and you either reject or fail to reject the null hypothesis. So let's take a look at an example. So here we have, in this example, 5 different types of cancer. You have stomach, bronchial, colon, ovarian, breast cancer. The numbers that you see here are the number of days the patient with the advanced stage of cancer survived. And so you diagnose this with stomach cancer and then survive for 124 days after diagnosis. And the question is, are the average survival days for these different types of cancer the same? Are they equal to each other? And so we're going to perform this mind-numbing calculation. And here it is. So you take your 5 data sets, you find the count, the sum of the 5 columns, the sum squared, the mean, and the standard deviation. Now, keep in mind, the mean of these 5 data sets is what we're comparing. And we want to know, are the means equal? Are these equal within a certain tolerance? And you can see right away that this number over here is really large, right? That this cancer has a very large survival rate, where these cancers have a lower survival rate, or survival days, I should say, average number of days. And so are they statistically the same at a 1% threshold? That's what we're asking. Are these equal at a 1% threshold? And I'm looking at this and I'm saying, probably not, right? Just my gut feeling is saying probably not, because the scores are kind of different, but imagine that they were a little bit closer. And so we're going to go through and we're going to do this calculation. So here is the calculation for the degrees of freedom for the in-between treatments, the within treatments, and the total treatments. So if you add them all up, there's actually the degrees of freedom is one less than the total number, and then you split that up into these two. Here is the sum of the deviations squared for the between treatments, the within treatments, and the total treatments. So that is the sum of the deviation squared. If you take these values and you divide them, you get these. And then if you take these two and divide them, you get your F score. I know, right? Like you're already on YouTube searching other things, because this is crazy, right? This mathematics, it's very complicated. There's no way you would ever want to do this by hand. So I feel kind of bad about this, because there's a disconnect, right? Like you've got this data, and somewhere the mathematics becomes so overwhelming that you just disconnect. And you're like, just tell me what the F score is and tell me what the P value is. And advanced statistics is kind of like this, where you start to lose that intuition that we had when we were back in modules 4, 5, and 6, right? You could kind of figure out, well, the area is going to be something like this and blah, blah, blah. You kind of lose it with these massive calculations. But that's why it's advanced statistics. It's much more complicated. But the upshot is we have a p-value that we're going to compare to alpha, a threshold. And remember, our alpha was 1%. So this value comes in much less than alpha. So our alpha is 1%. We came in at 0.00029. And so that means we get to reject the null hypothesis. That means that the means of these 5 types of cancer, the mean survival days, are not equal. And I know you're saying, well, I could have told you that, but now we have statistical evidence at the 1% threshold that they are not equal. Now, there is a website that will do this for you, and here's the link to the website. Now, this website will do a one-way ANOVA calculation for you. So you take your data for treatment 1, you put it in here, category 2, category 3, category 4, category 5. Then you select your significance level and you hit calculate. And it does all of this magic for you. The first thing I would do is I would highlight the data and I would paste it into a spreadsheet, just like this. So here's my data set. So I'm going to copy this category number 1, copy paste. Category number 2, copy paste. Category number 3, copy paste. So now I've put all of my information into the correct columns for this website. And now I'm going to scroll down and I'm going to pick 5% as my threshold, and I'm just going to hit the calculate button. And it's done. So as I scroll down, here are all of the values. Here's the number of items. Here's the sum of the items. Here's the mean. So I've got a 12.3, I've got a 10.8, I got an 11.4. Are these statistically the same at the 5% threshold? Here's the sum squared, and here's the standard deviations. Here is SSB. Here is SSW. Here is the total. Here are the degrees of freedom. If you divide these two, you get MSB and MSW. And if you divide those numbers, you get an F score, a test statistic of 2.27. And then down below in the red text is your p-value. How these numbers were calculated, we're not asking you to understand that. If you want to go on to advanced statistics and understand how the numbers are calculated, that's fantastic. Go ahead and do that. Learn more about it, because it's very interesting how these are calculated. But for our purposes, for an introductory statistics course, I think we've given you enough of a framework where you can say, okay, I understand the concept behind this test score, and I understand the concept behind this p-value. I know I got to compare it to alpha and then either reject or fail to reject the null hypothesis. And so all of this then gets put back into this. So you're going to put your means in here. You're going to do your F ratio. And we could drop those numbers in here. So just to show you that this works, I'm going to put my F ratio in here. I'm going to take my p-value, copy and paste that into here. And now if I submit this, you'll see that those values are correct. And it would take you a very long time to do this problem by hand. And this really is sort of the end of the sidewalk for introductory statistics. This is where, and this is how more advanced statistics is done. You take your data, you copy and paste it into either a website or a specific software program, and you hit calculate. And the mathematics is already programmed in, and it just gives you the p-value. So our p-value is much less than the threshold. So therefore, we reject the null hypothesis and we say at least 2 of the means are not equal in those 5 types of cancer. At least 2 of them are not equal. And so then we could go in and we could do further analysis and we could say, well, how not equal are they? Are they really not equal or just kind of not equal? And which ones are they? And do a comparative. That's not what we're going to do. So this course does not pursue a test to determine how much the means are different. We're not going to do that. We're just going to say they're different, and that's all we know. And that's the end of our sidewalk. This is where our sidewalk ends. Now, if you wanted to do more advanced study, if you do take a more advanced statistics class, you may learn that there are different tests like the Dunking test, the Tukey test, Schiffy, Dunnett. There's a lot of different statistical tests that are done for specific types of data. So what we were interested in this class was providing you a generalized understanding of statistics. What are means and standard deviations and percentiles? What is a normal distribution and how is it used to test hypothesis and to determine a confidence interval? All of that stuff. That's what we were attempting to do in this introductory course. If you want to continue on studying statistics, you're probably going to be using statistical software packages like SPSS, Statistical Package for Social Science. If you're getting into more analytical math and science type stuff, you probably use SAS or Minitab or MathLab. These are all statistical packages. My favorite is R. And the reason I like R is because it is free. Many statistical classes that you take don't use Google Sheets, but instead they use R. R is extremely popular and it's extremely robust because it's open source. And so many people have contributed to it. If you move on to a more advanced stats class, then you will probably be required to know R. And it would help to have a little computer programming experience under your belt if you go into that field, because R, again, is very command line based. And this is sort of where computer science and math start to merge. This isn't algebra. This isn't solving for X. This is big time number crunching. You're doing a lot of complicated calculations, and a computer does that well. And so many times you'll find that advanced statistics classes are actually offered in a computer science division. And I'll tell you what, the job market for advanced statistics is huge. Like if you are able to do data analysis and advanced statistics, you can write your ticket. What is every web interface doing? What is Facebook and Twitter and Snapchat and Instagram? What are they all doing? They're scraping your data and analyzing it. How are they analyzing it? With statistics. So there's a lot to be said for this, but I'm going to get off my soapbox now because this is where, again, our sidewalk ends. Intro statistics kind of stops here, and this is where you get into more advanced stats. So I really do hope that you've enjoyed this introductory course in statistics and that you'll continue to seek things out. When you listen to politicians talking about data, what's their margin of error? What's their confidence interval? When you read articles in the paper, Is the graph skewed to present a certain point of view? Look at those axes. Be a more intelligent consumer and critic of information. That's what this course was specifically designed to get you to do.